In section 7.5, we're going to look at electric potential and electric potential difference due to point charges. Electric potential due to a point charge. The electric potential is inversely proportional to the distance from the charge and proportional to the amount of charge producing the field. We can say that as the distance from a charge increases, the electric potential decreases. And if we look at this graph, we can see this inverse relationship. We know that as R approaches infinity, the electric potential becomes zero. Electric potential near a point charge. The blue curve is for a positive point charge, and the red curve is for a negative point charge. Only charges in potential energy are important, so you must always be clear about choosing the reference point for potential energy. Electric potential is proportional to electric potential energy, so you may also pay attention to the reference point for electric potential. For example, when dealing with a point charge, follow the standard convention by choosing V equals 0 at an infinite distance from the source charge. Infinite distance represents a distance so far away that any potential produced by a charge is negligible for all intents and purposes. We can say that it's equal to 0. In many other problems, we choose Earth as V equals 0 because Earth conducts charge well. Put another way, the electric ground is the point where V equals 0. For two or more charges, use the superposition principle. Remember that electric potential of negative charges are negative and electric potentials of positive charges are positive. However, because electric potential is not a vector, the total electric potential of several point charges equals the algebraic sum of the electric potentials resulting from each of the individual charges and their specific distances from their locations. This actually makes solving the superposition principle a lot easier when we're adding the electric potential to find the total electric potential because we don't need to incorporate direction. Let's move to electric potential energy for 2 point charges. For a pair of charges, this potential energy is inversely proportional to the distance between the charges and directly proportional to the product of the 2 charges. We can summarize this statement with the equation electric potential energy is equal to kQ1 times Q2 over R. Now I want us to do a little bit of reviewing, and we know the relationship between work and energy. So just as an aside, so we can compare these values and help to fully understand this concept, we know that work is also equal to kQ1 Q2 over R, and kQ1 over R, this term right here, is equal to electric potential. So we can say that work is equal to Q times electric potential. Now again, this is just to help deepen our understanding of how these concepts are related, and we'll use them as we answer some of these questions. So, electric potential energy is equal to kQ1 Q2 over R. This is qualitatively very similar to the equation for Coulomb's law. And if you remember, Coulomb's law says electric force is equal to kQ1 Q2 over R squared. So the difference is that for electric potential energy, it varies as 1 over r, not 1 over r squared. If the charges are initially separated by a distance of ri and then brought together to a final separation of rf, then the change in potential energy is equal to the final potential energy minus the initial potential energy. So we can say that it's equal to kq1 q2 over r final minus kq1 q2 over r initial. Electric potential energy as a function of the separation r between two charges q1 and q2. This graph shows that relationship. The blue curve is for repulsive forces and the red curve is for an attractive force. Okay, time to tackle some sample problems. A point charge of 4 times 10 to the power of negative 8 coulombs is 4 meters due west from a second point charge with a charge of negative 1 times 10 to the power of negative 7 coulombs. So let's draw what this looks like. We have Q1, which is 4 meters west of Q2. We want to calculate the electric potential due to these charges at a point P 4 meters north of the first charge. So we want to find out the total electric potential here at point P, which is also 4 meters north of the first charge. So we know the distance between Q1 and P, but we can also find the distance between Q2 and P. And we can use Pythagorean theorem to find this value, r, which is equal to the square root of 4 squared plus 4 squared. So r is equal to 5.7 meters. Actually, I'm going to change that to 5.66 meters, keeping the correct number of significant digits. So first thing we'll do is find the electric potential at point P with respect to Q1. So electric potential is equal to K Q1 over R. And R, we are looking at this distance here, which is the distance between Q1 and P. Let's plug in our values. K is 8.99 times 10 to the power of 9 newtons times meters squared per coulomb squared. Q1 is 4 times 10 to the power of negative 8 coulombs. And we know that R, 1P, is 4 meters. If we punch this into our calculator, we get 8.99 times 10 to the power of 1 joules per coulomb. Let's do the same for Q2. We know the electric potential at Q2, at point P from Q2, which is this distance, 5.66 meters away, can be calculated using the equation KQ2 over R 2P. Let's plug in these values. That's 8.99 times 10 to the power of 9 newtons times meters squared per coulomb squared times 4 times 10 to the power of negative 8 coulombs divided by, oh, I apologize, just blindly copied in that value. What I meant to say was negative 1.00 times 10 to the power of negative 7 coulombs. And the distance is 5.66 meters. So V2, if we punch this into our calculator, we get negative 1.59 times 10 to the power of 2 joules per coulomb. We're going to use the superposition principle, which states that the total electric potential is equal to V1 plus V2. Because these are not vector quantities, we don't have to incorporate any magnitude or any direction rather, just the magnitude. So we put in 8.99 times 10 to the power of 1 joules per coulomb plus negative 1.59 times 10 to the power of 2 joules per coulomb. If we punch this in, we get a total electric potential of negative 69.0 joules per coulomb. Perfect. In part B, we want to find the work required to bring a third point charge of 2 times 10 to the power of negative 9 coulombs from infinity to point P. So, the work done is equal to the charge of 0.3 times the electric potential at a distance of infinity away minus the charge of 0.3 total as measured at point P. Now we know that as V approaches 0, the electric potential approaches 0. So this term cancels out, and we can find the work done simply by multiplying the charge, which is 2.0 times 10 to the power of negative 9 coulombs, times a total electric potential of 69 joules per coulomb. If we punch this in, we end up with 1.4 times 10 to the power of negative 7 joules. So the work done on the third point charge as it's brought from infinity to point P is 1.4 times 10 to the power of negative 7 joules. The positive value of W indicates that the electric field does work on the charge to increase the charge's kinetic energy as it approaches P. Okay. In sample problem number 2, we're going to find the electric potential energy in dynamics of charged particles, and we'll incorporate the law of conservation of energy as we do so. So we have our initial state and our final state. In our initial state, Q2 is at rest. In our final state, we want to determine the speed of Q2. So let's read the question. A point charge, Q1, of 2 times 10 to the power of negative 6 coulombs is initially at rest, a distance of 0.25 meters from a second charge with a charge of 8 times 10 to the power of negative 6 coulombs and a mass of 4 times 10 to the power of negative 9 kilograms. Both charges are positive. Charge Q1 remains fixed at the origin, whereas charge Q2 travels to the right upon release. Determine the speed of Q1 when it reaches a distance of 0.50 meters from Q1. Now, one thing to note, starts at a distance of 0.25 meters and ends up at a distance of 0.5 meters, so it's doubling its distance. Interesting to note, and we'll use that to help us solve this problem, basically moving to twice the distance. Okay, so let's start solving. We have the initial electric potential plus the initial kinetic energy is equal to the final electric potential plus the final kinetic energy. Now, since Q2 is at rest, this term, the initial kinetic energy, is 0. So we can replace these with equations. The initial electric potential is K Q1 Q2 over R1. The initial kinetic energy we said was 0. The final electric potential energy is K Q1 Q2 over, since it is twice as far away, we can simplify this by writing 2R1. It was initially 0.25 meters and now it's 0.50 meters. I'm going to erase this, but I just wanted you to see that. And what we want to find is the kinetic energy, or the final velocity rather, of Q2. Remembering that Q1 remains fixed. Okay, we want to solve for VF, so I'm going to bring this guy over the equal sign. We have K Q1 Q2 over R1 minus K Q1 Q2 over 2R1 equals 1/2 mv final squared. Now, K Q1 Q2 over R1 minus K Q1 Q2 over 2R1. This is equivalent to subtracting 1 minus 1/2. Hopefully you can see this. If you simplify this expression here, what you'll end up with is 1 minus 1/2 is 1/2. So you get K Q1 Q2 over 2R1 equals 1/2 mv final squared. Now we can solve for VF. It's equal to the square root of 2K Q1 Q2 over 2RM. The 2's will cancel out, and we can sub and solve. We get 8.99 times 10 to the power of 9. Q1 is 2 times 10 to the power of negative 6. Q2 is 8 times 10 to the power of negative 6. R is 0.25 meters. And M is 4 times 10 to the power of negative 9 kilograms. If you punch this into your calculator, you should get a final speed of 1.2 times 10 to the power of 4 meters per second. Therefore, the speed of charge 2, when it reaches a distance of 0.5 meters from the charge Q1, is 1.2 times 10 to the power of 4 meters per second. Okay. In sample problem 3, we're going to look at a head-on collision. Two particles, a proton with a charge of 1.6 times 10 to the power of negative 19 coulombs and a mass of 1.67 times 10 to the power of negative 27 kilograms, and an alpha particle, which is a helium-4 nucleus, with a charge of 3.20 times 10 to the power of negative 19 coulombs and a mass of 6.64 times 10 to the power of negative 27 kilograms. They're separated by an extremely large distance. As they approach each other along a straight line with initial speeds of 3 times 10 to the power of 6 meters per second each, calculate the separation of the particles when they are the closest to each other. So I'm going to start by listing what we know. We know Q1 is 1.6 times 10 to the power of negative 19 coulombs with a mass of 1.67 times 10 to the power of negative 27 kilograms. Q2 has a charge of 3.20 times 10 to the power of negative 19 coulombs and a mass of 6.64 times 10 to the power of negative 27 kilograms. We know that the initial speed of Q1 is equal to the initial speed of Q2, and that's 3 times 10 to the power of 6 meters per second. Okay, we're going to use the law of conservation of energy. We know that electric potential energy initial plus kinetic energy initial should equal electric potential energy final plus kinetic energy final. Since the two charges are at an extremely large distance away initially, we know that the electric potential energy is 0. So we have 1/2 m1 times v1 initial squared plus 1/2 m2 v2 initial squared. This is the total kinetic energy initially. And this will be equal to, in this situation, when they are infinitely close together, or as close together as possible, they will have no speed. So it will be equal to k q1 q2 over the final distance plus 0. I'm going to multiply both sides by 2 to simplify this. If we multiply this by 2, these will cancel out. And then we're going to multiply this by 2. So we end up with, and I'm just going to solve with this guy over here, 2k q1 q2 over r final is equal to m1 v1 initial squared plus m2 v2 initial squared. Okay, just to clarify this a little bit, I'll move that 0 over. Okay, now we want to solve for RF. This will test your skills of rearranging. RF is equal to 2k q1 q2 over m1 v1 initial squared plus m2 v2 initial squared. Hopefully you can see that as easily as I've shown it. We can sub and solve. We have 2 times 8.99 times 10 to the power of 9 newtons times meters squared per coulomb squared times Q1, which is 1.60 times 10 to the power of negative 19 coulombs. Q2, which is 3.20 times 10 to the power of negative 19 coulombs, divided by, and meticulously we're putting in the correct values. M1 is 1.67 times 10 to the power of negative 27 kilograms with an initial speed of 3 times 10 to the power of 6 meters per second. Don't forget to square the speed. Plus M2 is 6.64 times 10 to the power of negative 27 kilograms. And again, the speed of Q2 is 3 times 10 to the power of 6 meters per second. Don't forget to square it. carefully punching this into your calculator, which in itself is a lesson in discipline, you should end up with a distance of 1.23 times 10 to the power of negative 14 meters. Therefore, the minimum separation of the proton and the alpha particle, when they are approaching each other with a speed of 3 meters per second, 3 times 10 to the power of 6 meters per second, they will reach a separation distance of 1.23 times 10 to the power of negative 14 meters. Okay, a few things for homework. I want you to try practice problems 1 to 4, review questions 1 to 8, but I also want you to read section 7.6. One of the most important experiments in the history of physics is the Millikan oil drop experiment. Your job is to read through this section. You don't need any of my help doing so. And I want you to summarize Millikan's experiment and his findings. Good luck.